Let's step back for a moment and take a quick review of some of the ideas we've been exploring on the subject of AVO, and you'll find a lot of these. You'll find all these videos in the AVO playlist. We, if you look at the titles here, we talked about bright spots and DHIs using Domenico's work, introduced the use of amplitude variation with offset using Ostrander's paper. We've talked about the different approximations that can be used, approximations of the Zoepritz equations that can be used to illustrate how amplitude varies with offset, two-term, three-term, Aki-Richards and Bortfeld approximations, the gradient intercept form of the Aki-Richards relationship, which is shown over here, where we plot the reflection amplitude versus sine squared of theta, and we see that the amplitude variation with offset takes on a linear behavior in this particular case. We'll come back to that, but now let's just kind of recap the thread of ideas that we've been pursuing as we've moved from topic to topic here. Now in this plot on the left, this is based on the ideas of Domenico. Domenico's paper goes back in the 1970s, mid-1970s, and for a long time the idea of bright spot detection, direct hydrocarbon indicators, the bright spot, was used as the basis for locating prospects for drilling, particularly in the Gulf of Mexico. This was quite a common practice, but it was quickly realized in this plot over here, for example, if you look, we've got reflection coefficient versus water saturation, and at 100% water saturation we've got pretty low reflection coefficients between the bounding interval and the gas sand that we're seeing over here. And it only required the addition of a small amount of gas in order to produce a significant drop in the reflection coefficient within the gas sand. So we would see a negative impedance contrast, a rather large one, associated with a rather small 5 to 10% gas saturation within the gas sand, and we'd get these large anomalies. And so people found out pretty quickly, when you drill into these things, you might not necessarily have an economic prospect. There may not be as much gas in there as you would like, obviously. Now this section that we've been looking at, we've talked a little bit about the normal incidence seismic section, so we can't see individual traces in here, but the traces in this view are what we've been referring to as stacked seismic traces or normal incidence seismic traces, and so on. Now there were some issues that we brought up about the normal incidence seismogram, and these are common midpoint gathers, the two on the left that we see here. And what that means is that if we look from source to receiver, or source to receiver, that all these source to receiver combinations share a common midpoint, and they may or may not have a common reflection point. In particular, they do not have a common reflection point when the layer is dipping, so that the events that you record on your receivers from the different shots, although they share a common midpoint in this case, the information that's coming back to the receivers at the surface or in the marine environment are coming from different points, different regions in the subsurface. So we see these ray paths walk up dip. And so these two diagrams over here, they have a common midpoint in both cases. They do not necessarily have a common depth point, as you can see over here when the layer dips. We're also assuming that we're looking at isotropic velocity distribution within the layers overlying the gas sand, because if we had high to low velocity as we came across the gather, we would get some additional distortions in the ray paths, and we would not have a common depth point. And we obviously don't have a common depth point here. Now, processors, if they have the information, all the information that they need, they can sort through the data, correct it, and come up with combinations of source and receiver that provide information from a common depth point or a common reflection point. And this is ideally what we'd like to have when we're talking about amplitude variation with offset. We'd like to have all of our traces in the gather, we'd like for those traces to be providing information from a common reflection point. Now, in this case, obviously, as we walk up dip, we're probably going to be seeing changes in compressional wave, shear wave, and density, compressional, shear wave velocity, and density that are associated with changes in stratigraphy, perhaps in this within the reservoir interval. In this case, we are hopefully looking at a region which is roughly the size of a Fresnel zone, and perhaps in terms of thickness about half the tuning thickness. And even within this volume, we expect to see some influence from local property variations, so that our logs, our sonic log, density logs, and so on that cut through the horizon at this point may show something a little bit different than what we're observing in the seismic. So all those variables come into play in how we interpret the AVO response. Now over here we're just pointing out that when these traces in the gather are stacked, we get what's referred to as a normal incidence ray path or a normal incidence seismogram. And you can see in this particular case we have a common midpoint, but if we follow that ray path down to this interface, the information that's getting stacked together and is displayed as a coincident source receiver record actually has data or responses that come from up dip of this particular location. Over here, this trace comes up to the surface. We can think of it as a normal incidence seismic trace, but again, it has, when we stack, we get information, we get the amplitude variations with offset, which we have seen can be kind of complex, and then we're also getting information from at least something that we hope is no larger than a Fresnel zone in diameter. So the AVO response then, if we think about stacking, this would be if we went out there and used our geophysical logs from a borehole, we'd calculate reflection coefficients, which would effectively be zero offset reflection coefficients, and these would be the zero offset reflection coefficients here for these different classes of anomalies. Now if we stack all the responses, the responses from all the traces in the gather, which have varying incidence angle, then we're going to be, we'll have a negative amplitude reflection out here at the longer offsets, larger incidence angles than we do at the zero offset. These are all going to get summed together, and instead of seeing a reflection that we might have predicted would be zero, we're going to see a reflection event that has some intermediate negative amplitude. Likewise, for these other events, the amplitude variation with offset, when we go through the stacking process, it's going to give us a trace. It's going to give us a reflection, which has reflection coefficient, which is a little bit more negative than we would predict based on the zero offset alone. Now these classes over here, we did talk about them, in this quick overview. We won't dwell on this, but the class 2 anomaly was one that would have a roughly zero amplitude, zero offset reflection coefficient, and the class 3 anomalies were ones that had a negative reflection coefficient, but in both class 2 and 3 cases, the amplitude continues to decrease with offset, becomes more negative with offset. So we discussed the Shuey 2-term and 3-term approximation. This is one form of that, which includes the Poisson's ratio. This is another form which is presented in terms of an intercept and gradient format. This would be the curvature term. We talked about this and spent considerable time on that. The Aki-Richards formulation that we also talked about at considerable length was used some different notation depending on the papers that you were looking at. Delta alpha over alpha would just be the change in the compressional wave velocity divided by the average of the compressional wave velocity, and then delta beta over beta for the shear wave, and delta rho over rho for the densities. Now, Russell typically refers to these as reflection coefficients of a property. In this case, the property being the compressional wave velocity, the shear wave velocity, or the density. So he's thinking about it in more general terms. And so you'll often see this representation not truly the reflection coefficient because we don't have the densities, we don't have the impedances here in these expressions, but nonetheless in a reflection coefficient format. Now down here we have the Bortfeld approximation. This looks quite a bit different than the Aki-Richards approximation, and you can see the presence of these natural logs in the computation of amplitude variation with offset. And if we look at the Bortfeld approximation, we have these two terms, and this first term is referred to as the fluid term, and you can see that it increases. The amplitude increases with offset. The rigidity term, on the other hand, is a term which decreases with offset, and of course they do get combined, and so that we see that the total amplitude variation with incidence angle drops a bit and then begins to rise back up at angles greater than about 40 degrees in this case, and this diagram was put together for 100% water saturation. Now here we're just taking a look at the kind of a close-up look at the Aki-Richards formulation, and we have it in this form here, general form, where r of theta is equal to a plus b sine squared theta plus c tan squared theta sine squared theta. So this would be the intercept, zero offset reflection coefficient. This would be the gradient, and A and B and C are defined down here. We talked a little bit about that, and again we talked about this kind of general form of the notation that was being used at you see not only in Castagna's work but in others as well. And these classes that we talked about that are based on the intercept gradient analysis, here we're plotting the reflection coefficient as a function of sine squared theta. We get these different classes as we mentioned, class 1, 2, and 3. Class 2 being, where a case where the zero offset reflection coefficient is 0, class 1 positive, class 3 negative, but in all cases the amplitudes drop with offset or become increasingly negative in the case of class 3, drop into the negative from 0, and may cross from positive to negative in the case of class 1. There were a couple other classes that were discussed, and we came up on our own here with this potential additional class, class 4. And here you can see where the intercept gradient analysis, we can take a look at the responses that we see. We can plot them up in this intercept gradient plot. we can see that class 1 falls over here, negative gradient, negative positive intercept. Class 2, 0 intercept or 0, almost 0 reflection coefficient. But again, dropping, negative gradient. Class 3, negative gradient, negative 0 offset reflection coefficient. And then we have this speculative class 5, and then here are the class 4 events that we see that start off and increase have increased or less of a negative reflection coefficient with increased incidence angle. So these are topics that we discussed in these first 6 videos, and so we've just kind of we're taking a look at where we've been and trying to put things perhaps into a little bit of context, pull ideas together, show where we've been, and this overview here will continue on with we'll look at the AVO relationship to the Lam-A parameters, lambda and mu, or specifically lambda rho and mu rho. So I hope this is kind of a useful conversation or reflection on the general concepts and the order in which we've been discussing them, and hopefully this helps pull things together. So thanks for joining us, and we'll continue with this next time.